So we've seen how we can use the Hough transform to find some very simple shapes that can be described with a small number of parameters. Now let's take a look at how you can generalize the Hough transform to find more complex shapes that cannot be expressed using an equation. So this is the generalized Hough transform. And so let's assume that this is the shape that's given to us. And the first thing you're going to do is define what's called a reference point. So it turns out that when you eventually end up applying the generalized Hough transform and you're trying to find this particular object, you're going to be voting for xc and yc. In other words, your cumulative array has the parameters xc, yc. If you find an xc, yc that has a large vote, then you have found this object, and you know where this object lies because you know where it is with respect to xc, yc. In other words, what I'm going to describe right now is the work you need to do a priori, offline, before you apply the generalized Hough transform. So here's what we do. We define xc, yc, and then this is again offline. For each point on the object's boundary, we're going to assume that we have the edge direction at that point. And that's phi I. So in this particular case, for Hough transform to work, we are assuming that we have not only good edge location, position, but also very accurate edge direction information as well. So this is phi I. And now we're going to represent this point, again, all this is offline, with respect to the reference point xc, yc. And we can do that using two numbers. We'll use it using the vector r. We'll do that using the vector r. And r has two numbers. One is the length r from the distance between xc, yc and the point. And the second is the angle that that line makes with respect to the horizontal axis, which is alpha. So you have rki. I corresponds to the point with the orientation phi I, and k because you may have multiple such points, and that's this tuple right here, which includes rk, the distance, and alpha k, which is the angle right here. And the reason you might have multiple points is that you might come around the object and find the same edge direction here, which is phi I, and that has a different vector r associated with it. So offline, you're going to run around the boundary of this object after defining the reference point, and you're going to create a table, and this is what we call the phi table, where on the left side, the index is going to be your edge direction, and the entry on the right side are all the r vectors associated with that edge direction. And that's what we'll call the Hough model associated with this object. An object that cannot be described with an equation, but can be represented in a discrete form using this table. This is the model of the object. So now we can use this model in an application to find the object in an image. So let's say that this is the image given to you, and we clearly see that we have the object right here. We also have some other points around it, maybe perhaps a lot more points. And our goal, once again, is to find the location of the reference point if indeed the object lies in the image. So we're going to create an accumulator array, A, xc, yc, which corresponds to the reference point. That's this accumulator array. And now we set the accumulator array to 0. And now for each point, remember at each point we have xi, yi, the location of the point, but you also have the direction of the edge. So we take this edge direction and we go into our phi table and we look at all the r's associated, the vectors are associated with that particular edge direction, and use those vectors to vote in the accumulator array. That is, we can compute the locations of xc and yc, meaning to say that if indeed this point xi, yi happens to lie on this object, meaning that the object is present in the image and xi, yi lies on that object, then you are indeed you're voting for the correct location of xc, yc. And you may have multiple such votes for any given point xi, yi, because for any given phi, as you know, you may have multiple entries in your phi table. So you go in and you vote, and you repeat this process for every xi, yi, phi, and you end up with a bunch of votes in your accumulator array. And the maxima here, once again, would correspond to the location of xc, yc. So if this is the point where you get a maximum number of votes, and if that maximum is large enough, then you can claim that you found the location of xc, yc. So let's see how this works out for some simple images. These are the models that we're working with on the left, a leaf and a cat. We create phi tables for each one of them. And these are the images we are going to use to recognize or find these models in. And indeed, you find that in Hough space, that is the accumulator array for these two cases, you see the peaks appearing exactly where you would expect them to appear. There's a leaf here, here, and here. This one, and this one. You get strong peaks there. And there's a cat right here as well. So that is your generalized Hough transform. And now you can imagine adding more parameters to the problem. At some point, it gets unmanageable in terms of memory and in terms of computations. But in theory, you can do this. If you said, well, I know what the object looks like, but I don't know what the size and the rotation of the object is going to be in the image. It could have some scale, s, size, s, and rotation, theta. You can add those as parameters to your accumulator array. So now you've gone from a two-dimensional accumulator array to a four-dimensional accumulator array. And now for any given point xi, yi, with edge direction phi I, you would go in and vote for your accumulator array, your reference point locations xc, yc, but you're voting in four-dimensional space because you've got to vote over many different scales and many different orientations or rotations as well. And so, in theory, this is an approach that one could take, but it should be clear that it requires a huge amount of memory and is computationally very expensive. So at some point, the generalized Hough transform with more parameters such as scale and rotation ends up being simply impractical. So some comments on the Hough transform in general. What's nice about it is that it works on disconnected edges. It is relatively insensitive to occlusion and noise in the sense that as long as you have enough edges that actually lie on the boundary of the object, you're not going to be as affected by extraneous data or even noise for that matter. And then we know that it works extremely well for lines and circles, simple shapes with a small number of parameters. And it can work on complex shapes using the generalized Hough transform, but at some point, there is a trade-off between work that you do in your image space versus the work that you need to do in your parameter space. So when you looked at the generalized Hough transform, which included scale and orientation and so on, you see that very quickly the problem becomes unmanageable in terms of memory and in terms of computations. So for simple parametric forms, the Hough transform is a very elegant, very useful technique. For more complex problems, it is not that practical.